Hey guys, welcome back to today's lesson. We are today talking about solving equations by backtracking. We're going to actually talk a little bit first about equations themselves because there's a lot of information I find students have misunderstandings about with equations. Today's mindset message is that math makes sense. I'm just reminding you of this again. Remember, math makes sense and you should expect it to. Sure, it's going to be hard sometimes. It'll be so frustrating that you might want to just throw it away for a minute or a while and maybe come back to it later. That stuff happens. When you're learning tough stuff, it happens. But remember, it does make sense and you can do it. We have two learning goals today. First is to understand the relationship between an equation and its solutions. So we're going to start talking about equations first, and then we're going to look at actually solving equations by using backtracking. Your prior knowledge would be remembering what variables and expressions are that we've been learning. We did learn about the backtracking method a little bit with number tricks, so remembering that is really important for today. And then just remembering about opposite operations and that they reverse each other, like our last lesson said. They undo each other. So for example, addition and subtraction undo each other. Multiplication and division undo each other. Let's go ahead and dive in now. First things first is a definition. An equation it's a math sentence basically, and it states that two quantities are equal, okay? And remember, quantities can be numbers or expressions. And I want you to remember, a variable or an expression still stands for a number. It's just allowed to be different things depending on what number we choose for that variable, right? So they still represent numbers. And another thing that I find with students is sometimes they get confused between if they should solve something or not. But if you're even going to consider solving an equation, you need to have an equal sign. An equation always has an equal sign, and sometimes if you're just looking at an expression, I find that students get a little bit confused with that. So let's go ahead and talk about three main categories for equations. An equation can be always true, just no matter what. So here's some examples of that. This one's kind of basic, but if I have 2 plus 5 equals 7, you probably agree with me that that's just true. It's never not true, right? Or another one with variables would be something like x times x equals x squared. The reason for this, mathematicians will say this is just because that's the definition of squared. Remember how when we square something, that just means multiplying by itself? So because that's just what it means to square, no matter what number x is, this is just always true. Now, most of the equations you've been used to working with in your life are sometimes true. So an example of a sometimes true equation, and this would just have one solution, so almost every number doesn't work, but there is one number that does. Let's say x plus 1 equals 6, right? Clearly, if you put 5 in here, 5 plus 1 equals 6, and so that is true for the number 5. But if I put a different starting number here, like 8 plus 1 is obviously not 6, right? So that's sometimes true. Here's another option, x squared equals 9. This is also sometimes true, because there's not just any number you can square to get 9, right? Some numbers that could square to get 9, 3 would square to get 9, but sometimes students forget about the fact that there's one more number that can square to get 9. Negative 3 squared. Now be careful here. If I want to represent negative 3 squared, we usually want to put parentheses here because that would mean the negatives included as part of the squaring. So this is equal to 9. Okay? So this happens to have only two solutions, but still it's just sometimes true. And then we have things that are just plain old not true. Again, if we did some obvious thing like this, that's clearly just not true, right? But if I had a variable, here's one that's not true. X plus 1 equals x. I do want you to start to get comfortable looking at things like this to be able to I encourage students to say it out loud actually. Is there a way that you can have a number plus 1 and then be itself again? Is there any way you can do that? You can move a number up 1 and then it'll be equal to itself? That doesn't make any sense, right? So this, no matter what, doesn't matter what number you try, it's just never going to be true, okay? So those are three important categories to know about equations. Now, these numbers that make equations true have a definition that is also important for you to note down today, and that they are called solutions, okay? So a solution to an equation is a number that, when you plug it in, meaning when you evaluate in the variable, it makes the equation true, okay? So for example, any number in this one will be a solution, because we said it's just always true, so every number that exists works. There's only one number that's a solution here. This one has two numbers that are solutions, right? 3 and -3. And then this one, there is no number that's a solution. So now that we have that background, let's go ahead and dive more into equations and then get some practice solving. Okay, so let's go ahead and dive deep into one single equation because there's actually a lot of important information about it. And you may think it's just like, no, I just need to solve it. But actually there's so much that you need to understand if we talk about it like this. Consider the equation 5x minus 11 equals 16. The reason I've ordered these questions the way they are is because there's a very specific type of thinking that it's going to build for us. So first of all, it's a good question to ask just guessing something like, is this a solution? It's really underrated in math class to guess things, but estimating and guessing is something mathematicians do all the time. And it just helps you figure out more information. It may be wrong, right? That's usually what's going to happen with the guess. But by guessing and checking, you learn about whatever it is, the problem is you're trying to solve. And it helps guide you in the right direction. So let's just ask, is x equals 7 a solution? Well, how could we check if x equals 7 is a solution? That just means let's go ahead and plug 7 in, so it says 5x minus 11 equals 16. I usually put a little question mark there because it just means, is that equal, right? But if we simplify this, we can see that this becomes 35 minus 11, which equals 24. And you can see that these are not equal, so my answer is no, it's not a solution, right? 24 is not that close to 16, you know? So let's move on to part B. How can we estimate the solution by guessing? Well, we've already started with a guess of 7, and 7 ended up with 24, which is a little too high. So it might be a good idea, and this is an important strategy with solving problems. So I made a guess, it didn't work. What if I make another guess that's nearby that guess? And you can think, should I adjust this 7? Should I go up or should I go down? Different ways you could think about it. Notice that we're subtracting 11 here, and the 24 was too high. I almost think we might want to try going down. Maybe that'll get better. Okay, so the answer to start this is try adjusting your guesses. That makes sense? We took one guess and we're going to adjust our guesses. So we know that 7 gave me 24. What if I try 6? If I plug 6 in here, 5 times 6 minus 11 is equal to, I guess maybe I'll do that over here. 5 times 6. You know what? This will even be better if I do it this way, actually. This was 5 times 7 minus 11, and that gave me 24. This is 5 times 6 minus 11, and that's 30 minus 11, which gives me 19. Hey, I'm closer to 16, aren't I? Let's keep going down. You see I'm being methodical with my guessing? It's such an important skill, and we don't think about that very often. This becomes 5 times 5 minus 11 when I plug that in. And that's 25 minus 11, which is 14, which, wait a minute, we're now too low. So this right here is too high. This right here is too low. What's a conclusion we could come to based on this? Because if you notice here, 5 was too low, 6 was too high. Neither of them is exactly the solution, but the actual outcome we want is somewhere in between, right? So the solution to this must not be a nice whole number. It's going to be something between 5 and 6. Really try to make sense of this. This is an important skill, okay? But lucky for us that backtracking can actually find the exact solution, this method that we're focusing on today, to this equation. So I'm going to think about it like we did before with like the little machines, or thinking of it like a number trick and reversing. So if we see these steps, I choose a number, multiply 5, subtract 11, and I get 16, right? So what we're saying is x goes through this machine, and we multiply by 5, and then we minus 11, and out came 16. How do I go backwards through this machine, right? I'm going to take this 16, and I'm going to undo this one, which is going to be plus 11, and then undo this one, which is going to divide by 5, and then I'm going to get out what I started with. So let's do that. 16 plus 11 is 27, and 27 divided by 5, that's what I get. You can certainly leave this. 27 over 5 is a single number. Now if you wanted to, you could actually divide that, and you're going to get 5.2. And that matches what we thought. We thought it was going to be between 5 and 6, and it is. It's 5.2. So that's the method of backtracking. I know many of you have actually learned to show your steps a very specific way to solve an equation. We'll talk about that like standard ways soon, but for now I really want you to get the hang of the concepts here. Let's move on to a couple more examples to illustrate backtracking, and then that'll be it for us today. Okay, so here's some real practice for you to do some backtracking. One comment before I have you pause and do it on your own. A lot of times, I think your teachers try to make you show your steps and everything for everything. I'm actually curious, if you want to, in your practice right now, I want you to see if you can solve these in your head. And if you can just try to solve it and put the answer down, and we'll check the answers. And then if you need to put out the steps, or if you need to list out like a machine like I did, or write it like a number trick, any way like that works for you is totally okay to use. What I'm going to do after you pause the video is I'm just going to give you the answer for now, since there's many ways you could do it, okay? So go ahead and pause right now and try to take a stab at these yourself. This one's going to be a little trickier because there's going to be 3 steps, but you can do it. And we'll come back together. Go ahead. Okay, so let's check our answers. This is just one step, dividing by 3, so I just need to undo by multiplying my ending number by 3, right? So we can see the solution, m equals 12. For this one, this has 2 steps. Choose a number, multiply 2, and then add 5, and we end with 11. So I need to undo, remember shoes and socks, right? So 11, if I subtract 5 is 6, and divide by 2, so x equals 3. You maybe could have also just checked that by plugging numbers in your head. That's totally okay to do on those ones if you can. And this one here, if you add 1, you get 8. And then you need to multiply by 4. So y equals 8 times 4, so 32. Okay, check that one. And then this one's a little bit of a doozy, right? But let's just think. To reverse this, 2 times 9, because dividing by 9 was the last thing we did. Again, if you need to list it as a number trick or with those like machines or whatever, then you can do that and go backwards. But that's 18, and then divide by 6 would be next. Make sure you're following the right order. You wouldn't add 3 until the very end. So, and then 18 divided by 6 is 3 plus 3, so r equals 6 actually. So go ahead and check those. Remember, you can always connect with me if you want to talk about those any further. Okay, our last exercise for today is actually going to involve an equation that has 2 variables, which that's kind of weird, because that means we need to have 2 numbers that work independently to be able to make it true. So this equation is 3p minus 4q equals 10. Okay? So the cool thing is, if we set one number at a specific thing, so in this case we said if q equals 5, find the value of p. So notice something here. If q equals 5, then the equation becomes 3p minus 4 times 5 equals 10. Do you see that? But then 4 times 5 is just 20. Oh, now that just looks like one of the equations we've been working with backtracking. And if you solve this in reverse, remember it's choose a number times 3 minus 20, and we end with 10. So we'd add 20, and that would give me 30, and then we have 3p equals 30. So we have 3 times the number equals 30. Remember, a lot of this we're trying to get the hang of, like, working this out in our heads, and I'm not going to give you any crazy numbers right now. And that just means we can see that p equals 10 there. 3 times 10 is 30. So why don't you take a stab at part B yourself, and then we'll do it together, and we'll be done. Okay, let's check your work here. So this becomes 3p minus 4 times negative 2 equals 10. So we get 3p minus, oh wait a minute, negative 4 times negative 2. You got to be really careful with our signs here, with our negatives. That's going to turn into a plus 8 here. So you may want to check your work on that in case you accidentally missed it. And then if we backtrack this, then I get 3p equals, I need to subtract 8, equals 2. And then, yeah, this isn't really the greatest number because I need to divide by 3, but p equals 2 divided by 3. That's still okay and it works. So, that is it for this lesson on backtracking today. Again, happy math, and we will see you in our next lesson.